After solving an interesting question, now let's move on to the 10th question, where you have a very big molecule and you have hydrogenated this in the presence of a metal palladium or carbon. This is palladium, and you have supplied 3 equivalents of hydrogen, and you observe that the central 6-membered ring, which is benzene like molecule, is hydrogenated completely, but other 3, these ones, are not affected. Now you are asked to explain the reason for it. Now to solve this or to explain the reason, identify this molecule given to you very carefully. You can see that these 3 pi bonds are in resonance with each other, that is, they are completely delocalized, and also the same is the case for this one and this one and this one, as said before, and also for this one. So one of the possible resonating structures is, I'll write out the structure for you. You have 4-membered ring here. So if you observe the given molecule, it has 4 6-membered rings and 3 4-membered rings. Now it's one of the structure is like this one, if you see, and if you carefully observe, notice that, consider this one, it has planarity and it is completely conjugated, and it has 6 pi electrons, which is 4n plus 2, where n is equal to 1, it's like benzene. So we can say that this is aromatic compound, as we have discussed these conditions before, and the same is the case for this one, for this one, for all these 6-membered rings. Now carefully observe the 4-membered rings here, these ones, these one, it's like cyclobutadiene, right? Yeah, it is planar, it is completely conjugated, and it has 4 pi electrons. It satisfies the condition for the anti-aromatic compounds, and so it is anti-aromatic. And we have also told that aromatic compounds are stable and anti-aromatic compounds are unstable. So what is happening is, this resonating structure, this one is responsible for anti-aromaticity of all these 3 4-membered rings, whereas the other ones, the extreme 6-membered rings like this one or this one or this one, are responsible for this anti-aromaticity of this 4-membered ring. Only one ring, that is, this is responsible for anti-aromaticity of this ring, and this ring is responsible for anti-aromaticity for this ring. But if you take the central one, this one, it is responsible, that is, it's giving the anti-aromaticity for all these 3 rings. So in other words, this molecule, though it is stable, it's making the other 3 molecules unstable, that is, these things here, the 3 4-membered rings. So to get rid of this instability, what happens is, these hydrogens attack on this, and you will get a stable molecule then, even then, because the structure is given to you here. See that it is aromatic, and this one is also aromatic, and this one even is aromatic. So you have finally got aromaticity, and it is stable one. So the reason is clear that why hydrogens attack on this central 6-membered ring and not on this one, because this is giving anti-aromaticity to all these rings, and it is responsible for unstability of these 4 membered rings. So that's an interesting question, right? Now with this we end this question. Let's move to our next question. Students, after solving an interesting question on the application of aromaticity and anti-aromaticity, now let's move on to the next question, where you have benzene and benzene substituted with OCH3 and benzene substituted with NO2 in presence of sodium and liquid ammonium in the solvent ethanol to give products X, Y and Z. Now you are asked to find out what X, Y, Z are. So the reagent given to us, which is sodium and liquid ammonia, suggests that it is bridge reduction. We have already learned this in chapters alkyne, that is how they convert alkynes to trans-alkene. And the mechanism for this is same. First we start up with benzene. This undergoes homolytic cleavage. You get free radicals, and we know that sodium gives Na plus electrons. Since it's a metal, it loses its electrons, and this radical takes up electrons. This will give you a radical here and negative charge here. Now we were also told that this is stable in anti-conformation, that is this anion radical, or you can call it as radical anion 2, is stable in its anti-conformation. Now it is obtained by shifting this bond this direction. So you are going to get a vacant negative charge here and a free radical here. Now you have solvent as ethanol. Now it takes up hydrogen from this ethanol. You are going to get hydrogen here. You initially have one more hydrogen here. Now we have a free radical here, and it takes one more electron to give a carbanion. We have 2 hydrogens here. Now the same thing happens, that is it takes hydrogen from ethanol, and you are going to get this product. This one is very simple one. Now let's see what happens if benzene is substituted. Let's say G is substituent for benzene. There are 2 cases for G, it being ring activator and orthoparadirector, that is, and ring deactivator. Yes, which is not orthoparadirector and it is less metadirector. And these are for electrophilic aromatic substitutions, as we have already discussed them before. Now first look into the first case where you have orthoparadirector, and that's given in the second case for us, where we have given OCH3 as substituent, and I am writing an example here, OCH3 G, G equal to OCH3. Now first thing, the same one which we do, we get free radicals here. Now you have electrons in the solution. This electron can add up first either this place, say side A, or at side B. Now we tax on side A, you will get this one, G here, negative charge here and radical here. If you tax on side B, you will get G here radical here, and negative charge here. Note that this OCH3 being ring activator and orthopara director creates more negative charge at orthopara directions. That is, this gives negative charge at this position, this position, this position. Now you can see that this got negative charge from electrons, but it is even getting negative charge from this OCH3. As a result of it, the negative charge on it is increasing, so thereby it's becoming less stable, and so it is not formed, and you have obtained this one. Now the next thing to do is to make this anti. Now let's see here. You have G negative charge and radical here. Now this radical and this anion are obtained anti by shifting the bond in this direction, this bond. So you are going to get a substituted G to benzene and two double bonds, radical, anion. Now the same thing happens. First it takes 1 mole of ethanol, this gets hydrogen H, that is, it will get converted to this hydrogen here, it also has hydrogen here, and this is our substituent G. Now this takes 1 more electron, and finally it takes hydrogen from ethanol, where R is Et, and you are going to get the product as, let's write down a final product where you have G as OCH3. You will get hydrogens here and here. Let's come to the second part where we have a ring deactivator, say NO2, as given in the example, that is G is equal to NO2. Now let's consider the structure of nitrobenzene and let's investigate why this NO2 is ring deactivator, O minus plus. Now this oxygen, being more electronegative than nitrogen, takes up these electrons, and this nitrogen takes this bond pair because it's more electronegative than carbon, and you are going to get. Also note that the lone pairs of nitrogen are shared with oxygen. A positive charge at ortho position, O minus, yeah, this one, and this is also delocalized, this positive charge, by shifting this bond in this direction. You get the positive charge stands for there, and also this is delocalized to this ortho position. By shifting this bond this direction, like this one. Now you can see that this NO2 is creating positive charge at ortho para positions, hence we say that it is not favorable for an electrophile to approach this side. That's why we call it as ring deactivator and meta director. Now let's come to the question and try to figure out the mechanism for it. First we have NO2, and our first part is homolytic cleavage, and it will give a free radical on this carbon and this carbon. Now we have electrons here, say they can add at position A or side B. Now you can see that from the before mechanism you are getting a positive charge here, that is at ortho position. Now if you add electrons at ortho position, they are decreasing the positive charge by negative charge of electrons. So negative charge or addition of electrons at this position is stable and you have free radical here. Now the next step is making these two trans. It is obtained by shifting this bond this direction, and you are going to get NO2, a negative charge here and radical here. Now this will undergo series of steps as shown here. First this takes hydrogen from ETOH, and then this takes electron, and then the carbanion form here takes hydrogen from ETOH. All this is as shown here. The same thing happens, and finally you are going to get this one, NO2, where you have hydrogens here. Now let's quickly summarize what we have learned here. First thing is, we have shown the mechanism for bridge reduction, where we have shown the intermediate as anion radical, and we have shown that only 2 pi bonds are formed in the final product, and we have discussed various cases when we have a substituent on benzene ring. First we have seen what the cases are for ring activators like OCH3, and second for ring deactivators like NO2, and we have also discussed why NO2 is called ring deactivator or its method director. We have seen that it creates a positive charge at ortho and para positions, and finally we have seen the difference between the products obtained upon bridge reduction of this benzene, or in other words the addition of sodium and liquid ammonia for benzene for different substituents. We have seen the orientation of these bonds with respect to this substituent changes as it changes. Now